All right, good. Let's look at the problem from last section. This is a sequence of, it's given by this formula. Okay. Now, you take a look at this sequence, right? And just change the sign. Right? You can write down a few terms, right? It's like when n equals 1, when n equals 1, and that would be -1, then +2, -3, +4, -5, +6, keep going like that. So, so I think it's not monotonic because it's always go up and down, right? And it's not bounded, so you can take a absolute value, and clearly this go to infinity, right? So this is unbounded, yeah, it is unbounded, and it's unbounded, this sequence, and it's not monotonic, right? So that is my answer. Okay, it's unbounded. Okay, so the limit does not exist. Okay, does not exist. Even you cannot say the limit is infinity. However, the limit of the limit of absolute value, yeah, you can say doesn't exist, but you can also put a positive infinity there. Okay. Now, when we say limit exists, means it approaches a fixed finite number. Okay. In the generalized sense, sometimes we say the limit is going to be infinity. Okay. The reason we want to study sequence of numbers is because we really want to understand the infinite sum. Okay. Now let's begin with the following problem. This is actually is even from the math contest in the middle school. I'm surprised they use the concept of the infinite series. Okay, so this is a square, unit square. Then you divide it into 4 parts, and you shadow it. Okay. Okay. Then you divide this into 4 parts, and you change it. Okay. Then you just keep doing this procedure. What do you see there? You get infinite sequence of squares. Okay. So what is the total? What is the area? Total area of this shaded squares, right? Right. 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 So what is the shaded square? The total area. Then this is a unit square, right? So you can figure out the edge length first. So it's A1, that's A2, A3, and then keep it going, right? So A1 is going to be 1/2, right? A2 is going to be A1 divided by 2, it's 1/2 square, right? So everybody can figure it out. AN is 1/2 to the power n. Okay. So the area, okay, the total area of the first n squares, okay, is going to be, that's called Sn. That's going to be A1 square, right? A2 square, An square. So the students have to figure out what is the limit of this Sn, because you want to get to the total area for this infinite many squares. You have to make n as large as possible. So they have to know the concept of limit. But I saw this problem on the math contest, okay, for the middle school students. Okay, so yeah, so I put the 1/2 square here, this square, right? Right, and the one that's also square, right? So the question is how to combine into one fraction. Then you understand the limit, okay? Because the total area of all the squares should be the limit of the area of this first n squares, right? So the question is how to add them together, and this is it's pretty strange, right? So I can express in the following form. I square each term first. When I squared, sorry, I get 1/4, and this is a 1/4 square. This is a quarter cube. Okay, you know why? Because in general, 2 to the n square is going to be 2 to the 2n, which is going to be, I change this. Okay, so that's why it's going to be 1/4 to the nth power. Okay, so the general term is 1/4 to the nth power. All right, then we do need a formula to combine them. I'm going to talk about this formula later. Okay, this formula is going to be, you can take a quarter out, then they have begin with a 1. Right? Sorry. Now this is n minus 1. So the formula says that it is going to be 1 minus 1 over 1/4 to n's power minus 1/4. Okay, so if we can combine into this, and the denominator right now, after simplifying it, 4 times 1 minus 1/4 is just 3. Okay, because of 4 minus 1. Right. Okay, so this, the sum of first n squares is going to be this number. Okay, and this is always less than 1/3, right? And you will see that this sequence is getting close to 1/3 as n approaches infinity, right? Because the limit of, since the limit as n approaches infinity, 1/4 to the nth power is 0. Okay, so that's why. So the total sum the total area of all square is going to be the limit as n approaches infinity, which is just 1/3. Right? The limit, the limit includes all the squares. They're getting smaller and smaller and smaller. Okay, so let's go back to the picture. Okay, so this here, we needed the concept of limit here. Okay, I don't know why they ask the students in middle school to solve this problem. So you have everybody knows the formula for the squares, okay? For the area of the square, yeah. So you have an infinite many squares here, getting smaller, smaller, all the way, right, on the diagonal. The total area, okay, of all the squares, infinite many squares, is going to be the limit of the area of the first n squares. Right now it says 1/3. Okay, so this is a problem. Okay, so let's take a look at this series. Okay, we add them together, and it's n minus 1. Let's put n. So you have n terms here. I call it Sn, okay? Now, how can we combine them into one fraction? The idea is as follows. You multiply the sum by r, so you get r. The second term r times r is r squared. The third term is r cubed. And then the term before that will be rn minus 1. Then the last term is rn, r to the power n. Right? So this is a trick, yeah. This is a trick. So now you will see this is equation 1, that's equation 2. So equation 1 minus equation 2, I will get Sn minus Rs, n, right? And this side, all the terms, all the terms here will be gone. Okay, all the terms, those are the common terms that cancel out. Only left is this two. Okay, so then the left-hand side you factor it out, and then Sn is going to be 1 minus to the power n and 1 minus n. So you see, you get a simple form. Okay, now we know that if the absolute value r is less than 1, then the limit of r to the n should be 0. So in this case, the limit of Sn is going to be 1 over minus n, right? Because r to the n is 0. So in other words, if we have infinite terms, add them together, infinite terms, this should be equal to 1 over r. Okay? Okay. Right, so this is called the geometric series. Okay, yeah. So our notation, okay. Let's introduce a notation. Okay, if I write, this can be from capital N, okay, N in any. Okay, so this is defined to be, okay, the limit sigma n from capital N to k goes to infinity. Okay, so in other words, this is a limit, and the first term is a, if we begin with capital N, then ak plus 1 and ak, you have infinite terms. Okay. So if you use this notation, then infinite n from 1 or from 0, doesn't matter, right? So this is going to be 1 over minus. You can also, then when equals 0, then it's 1. You can also express it in another form. And start from 1, this r to the n minus 1. Okay. Okay. So it's not necessarily always the n starts from 1, n can start from 0. Okay. And the first term, just make sure it's going to be 1, r to the power 0. All right. Now, the reason this is called a geometric series. Okay. This is called geometric series. You know why it's called geometric series? It's from geometry, right? We just did the problem about. Okay. It's a geometric series. Okay. So when you see this notation, means it's infinite sum, the sum of infinite terms, which you viewed as a limit of the sum of finite many terms, first n terms. Right? And the next example is 0.9 bar. Now this actually, when we write it's a 0.09999, this is a limited concept because you cannot keep writing a digit 9. It's repeating, right? So why this is viewed as a limit is because 0.9, 0. Right? 0.9, 0.09, 0.009, and keep it going, right? That's right? So this actually is a series. It's a sum of infinite many terms. But these infinite many terms can be written in the form like that. Okay. So so you can take one common fact out. You get 1 over 10, 1 over 10 squared, 1 over 10 cubed, and keep in. So this is sum of infinite terms. So by the above formulas, it should be equal to 1 over 1 minus r. R is 10. Okay, let's simplify it. That is going to be, so the answer is 1. So actually, in fact, we conclude that this is nothing but equal to 1. Okay. Right. So this is identical, it's the same. 1 can be expressed as 0.99999. Okay, infinite many nines is actually just 1. Right. Right, so let's take a look at another problem. Yeah, sometimes you don't need to always take the constant out. Okay, for example, let's look at the most general case. And here's constant a. This is to the power, and let's use n here, right? So what does that mean? So this is going to be a to the r to the capital N, a capital N plus 1, right? And we assume that, I is less than 1, the absolute value. Now let's try to find out the formula for this. Okay. Yeah, you can look at the partial sum. Okay, so you can look at the partial sum. This is n to the power k. Okay, so a to the power n. So you have a to the r to the k, right? Right. So you take the first term out. Okay. And then you get a 1. Here's r. Here's r squared. Depends on how many. Here's k to the power n. Okay. So you have r to the k minus 1n. So you have this many terms, and those can be combined. It's 1 minus r k minus n plus 1. Okay. So since r absolute r is less than 1, right? And then this goes to 0 when k goes to infinity. So this approaches a to the r to n and 1 minus r. Okay. So I can write the first term divided by 1 minus r, because the limit because the limit is going to be this. Right. So all you have to do is just you can get this answer in a different way. Okay, you write down all the terms, right? Then although they're infringement terms, you can formally factor this out. And you know that this is going to be 1 over 1 minus I if absolute I is less than 1. Okay, so you can quickly get this. You can get the answer. Okay, so let's take a look at the next problem. This is from number 24 from the book. N start from 0, 3 to the n minus 1, and negative 2 to the power n. Okay. So you can express it in a slightly different way. I can 3 to the n minus 1 is going to be 3 to the n times 3 to the negative 1. So I have a 3 to the negative 1 here. And then this will be like a 3 over negative 2 to the power n. Okay. So the problem here, I is going to be negative 3 over 2. So the absolute I is going to be 3 over 2, which is greater than 1. So I'm not going to get a limit in this case. Okay. So this is divergent. Okay. Well, you can double check that. Okay. So in general, you can. Okay. So here's k, n start from 0, a to the power n, right? And we know that you have a plus a to the r, a to the r to the power k. So you take constant a out, then you get all the terms here, 1 plus r, all the way to r to the k. So you can combine them. Okay. The problem is that if absolute r is greater than 1, then the limit as k approaches infinity, r absolute value r to the power k plus 1 is actually infinity. However, if I is negative, the limit of r, then the limit, okay, of k to this one is not going to be a finite number, okay, does not exist. Okay, more precisely, if I is less than 0, less than negative 1, okay, and this is going to be positive infinity if I is greater than 1, okay. But in either case, it's called divergent. All right, so that's why that is the reason this limit k approaching infinity. This is the n start from 0, a to the power n. This is a notation for that limit. This one is divergent. Okay. Yeah, in this case. Okay. All right. All right, so take a look at the next problem, number 26. I think this is going to be divergent again. The reason is, whether I'm copied wrong. Yeah, this is divergent. Okay, the reason is, I can express it in a slightly different way. This is going to be, 2 to the power 2n minus 1, right? Is going to be 2 to the 2n divided by 2, right? It's going to be 4 to the n divided by 2. Then 6 divided by 2 is 3. Here's a 4 to the n, here's 3 to the n. Okay? Then okay, right? We already discussed in above, right? So here's I is going to be 4 over 3, which is greater than 1. So it's divergent. Actually, in this case, it's going to be positive infinity. It's divergent. Right? You're just using the above fact. Okay? And record the theorem. If we study from capital N, and this is R to the power N, right? Right? You have only two cases here. One is A over 1 minus A to the R capital N if R is less than 1, right? Because the first term is A to the R to the power N. And this is going to be positive infinity if I is greater than 1. Actually, it depends on the sign of A, okay? I should say, yeah, we can assume A is positive, okay? So in either case, it's divergent, okay? So I should just simply write the divergent. I don't want to make it wrong precise. Yeah, because otherwise I can, it's divergent. If basura I is greater than equal to 1, okay? Yeah, this is called geometric series, the most general case. Okay. Okay, let's do one more exercise. And start us from 4, and that is going to be negative 2 to the n minus 1, 3 to the n. Okay. All right. So the question is it convergent? And what is a limit if it's convergent? Yeah, you think about it, okay? I want you to try first. You can get answer from the above thing, about the formula, okay? You just figured out what is capital M, what is A, what is R. Okay, I hope you already figured out how to do it. And let's try. Okay, I'm going to express. I don't need to change the a. Okay, change it to 4. So n is start from 4. I think 2 to the power n is going to be 1 over 2 here. Right, here's negative n, here's 2 to the n, 3 to the n. So now I have n and n, that's the same power. Right? Here's 1/2, and this is going to be negative 2 over 3 to the power n. Okay, so compare with above, right? And capital N is 4, right? A is going to be 1/2, right? And I is going to be negative 2 over 3. Okay, so this is going to be A, right? A as the first term, right? So actually it's 1/2. Just write on the first term and divide by 1 minus R. Okay, so that's simplified. This will be 5 over 3, and this will be 1/2. It is positive, so 4 to the 2 to the 4th power, 3 to the 4th. So we have to simplify. Okay, 1/2. Yeah, let me do one more step. Okay. Okay. So I think the numerator is 8 times 3, 24. Okay. And the denominator, no, actually, 3 is also done. Okay. So that will be just only 8. It's 8. And then and 27 times 5, you can do the multiplication. So this is answer. This is answer. All right, now let's discuss a little bit more general, okay? Series, okay? We given, here's definition. We given a series, it's from capital N to infinity, okay? So you begin with A capital N, right? A capital N plus 1, and so on, right? You have infinity. This notation, okay, is viewed as a limit as n approach, as k, yeah, I use the k approaches infinity, and n, okay? And this term is also denoted by sk. So this is just limit of another sequence. Okay, sk is a finite sum. So you begin with capital N plus 1, and a to the power a, the case term. Okay, so this is called a finite sum. Okay, so you don't need a limit here, but if you take a limit of this finite sum, and this called, then the limit is denoted by this notation. Okay. If the limit exists, then we say this is a, yeah, this is called a series. Okay, this is called a series. So the series is convergent if the limit is finite, exists. Okay, so the series is convergent if the limit exists. Okay, if the limit exists, okay, that is the limit. Okay, limit is above the limit. All right, so now let's take a look at problem. Okay. Okay. So this is the sum of infinite terms. If you want to write down, that's going to be 1 times 2 here over 2 times 3, and just infinite terms. Now, yeah, This is also, this type of problems also shows up in the math contest, the middle school. You're surprised, yeah. So that was a problem in the math contest. Evaluate the sum and last year is 2020 and this year 2021. Okay, every year they probably give a similar problem. And the question is, how many terms here? 2020 terms. How do you add them together? You really need a good idea to do that. Otherwise, it takes a whole day, you cannot finish, maybe 2020 years. So, but if you know how to solve this problem, you have no trouble to find to find this series, the limit. Okay. All right. So the idea is that you make it more complicated than before you simplify. So each term, okay, each term will be the difference of this corresponding two terms. Okay. Okay. Actually, yeah. Okay. This will be separated to, okay, because when you combine them, the denominator will be 2 times 3. The numerator will be the difference of these two consecutive numbers, which is 1. And keep it going here, 2020 times 2021, right? It's separated as 2020 minus 1 over 2021. All the terms in the middle will be canceled out. So when you add them together, this just equal to 1 over 1 minus 1 over 2021. If you combine them, 2021 minus 1, so it's 2020 over 2021. All right, so this is a problem for the middle school kids. Okay, but if you got this idea, then you can easily solve the problem, about problem. Okay. All right, so take a look at the partial sum. N equals 1, right? Okay, so if you write down the details, the first terms will be similar, but the last term just change it to the 1 over k times k minus 1. So similarly, okay, similarly you can decompose each term into 2 terms. All the terms in the middle will be canceled out. They're all gone. So only the term left is 1 over k plus 1 minus 1 over k plus 1. Okay, and clearly the limit is going to be 1, right? So that answer is 1. So in other words, the sum of the infinite terms is 1, okay? It's just equal 1. Okay, in other words, this n equals 1 here, n times n. This is just equal 1. Every term is, the term actually is getting smaller and smaller, right? And but the sum of the infinite many terms is going to be 1. If you use a limiter, it's a concept limit. Yeah, so you can, if someday you can meet, you don't need it to 6th grade, 7th grade and 8th grade kids. You use this problem to test him whether he's good in math. Okay, that's what I do sometimes. Say, hey, he said, I'll get an A, I'm good. Okay, let's do this problem first. And if this fails, then I'm not going to destroy his confidence. But clearly, it's not good enough in number theory, dealing with the numbers. and he has to or she has to study this when she gets into college, because this is a chapter 11 problem, right? All right. All right, so let's take a look at the next problem. Study this series. Okay. So every term here is sum of the two terms. Okay. Okay, how do I do that? Well, you just look at the partial sum, trying to simplify it if possible. Okay. The partial sum are those terms. Okay. Let's write down all the terms. It's already separated right here, two terms, right? I can express in a slightly different way even. Then you have more troubles. Okay. Let's see. So the first term is going to be square root of 2 minus square root 1. The second term is square root 3 minus square root 2. The third term is square root 4 minus square root 3. And keep it going. The last term is square root k minus. Okay. Okay. Then you look at all the terms. What do you find out? You find out square root 2 is cancelled out and the square root 3 will be also cancelled out. So I have to be careful in the check. You find the square root k is cancelled out. The only term is left, only two terms is this one. And then clearly this goes to infinity as k approaches infinity. So my answer here is infinity. Okay. Okay. This is the limit as k approaches infinity, and this is going to be positive infinity. And you can say that divergent. Okay. Now, if you rationalize this term, this is actually going to be, okay? So if I give you the problem like that, maybe you have a trouble to figure it out. Okay, this is the same. You probably have to modify. Yeah, this is divergent again, because why? We maybe find another way to check that later, but because this is the same series as above, I just modify the nth term. I express this from difference to a fraction. Okay. All right. Now we come to another interesting theorem. Okay. You look at, yeah, given, sorry. Oops. Okay. Given a series, okay, n from capital N and Sn, An. Okay. Now I'm going to look at Sk. This is a partial sum. Okay. So you have A1, A to the N, right? And the last term, oops. This is a k minus 1, and here's a to the power k. If you look at these terms, this is actually sk minus 1, right? Okay. And now, so then in other words, I can express, yeah, let me simply write this. Okay, or AK is going to be SK minus SK minus. Okay, so if the limit of K goes to infinity, SK equals L exists, what you can conclude? You conclude that the n, the case term, okay, the case term is going to be the limit of the first term, which is L, the limit of the second term, right? This also implies the limit of K approaches infinity, SK minus 1 is also equal to L, right? So that's why L minus L, that should be 0. So the case term must approach 0. This is a very important result. Okay? We can use that to check whether the series is divergent or convergent. If it's convergent, the limit is 0. So if the limit is not equal to 0, then it's divergent. So what? Let me state that. If this is a convergent, then the limit should be 0. Now, in other words, okay, this is two parts that are equivalent. If the limit is not going to be 0, maybe it does not exist, then this series is divergent, right? Clear, right? So let's understand the logic. If the series is convergent, I just showed that the partial sum approaches some number, finite number. So that based on the above argument, you see the nth term must approach 0. And so if the nth term does not approach 0, then the series is divergent. So this is called nth term test. Nth term test for divergence. Okay, this is a part. It's called nth term test. Nth term test for divergence. Okay, you cannot use that to prove the series is convergent. You can only use that to prove this guy is divergent. So you say someone is good. Oh, this is a good bad guy, right? By definition, he's good at everything, right? If one day he commit a crime, we don't say he's a good guy. At least by definition, he commit a crime, right? So in order to prove he's not a good guy, you have to find out one day he committed a crime. Right. So this is how do you solve it, right? So, but it's but the nth term the common mistakes made by students is that if they see the limit of the nth term approaches 0, then even without looking at any theorem in the book, just jump to the conclusion this is convergent. Okay, and actually it's wrong. Okay, so let's take a look at an example. Okay. You look at this, right? I want to check whether this is a convergent or divergent. So clearly the limit of the nth term is going to be 1. That's obvious, right? Why it's 1? Because n minus 1 over n plus 1 is going to be 1 over 1 minus n or 1 over 1 plus. It divides the numerator and the denominator by n. So that's why the limit is 1 minus 0 over 1 plus 0, which is 1. So the nth term is 1. Therefore, it is divergent. Okay? I just say it is divergent since the limit of the nth term is 1. Okay? It's not going to be 0. Sometimes even the limit doesn't exist, right? But the limit exists here, and it's not going to win. Okay. Just because you are adding, every time you are adding a number very close to 1, of course you're going to get bigger, 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 right? And though it's divergent, actually the infinite series is infinity. Okay, the sum of infinite terms is infinity. Okay, so this is divergent. And similarly, you can look at this problem here and start from 1 n square minus 2n plus 5. Okay, don't worry about the denominator. The denominator never be 0. Okay, it's always positive. Okay, and since the limit of the nth term is going to be 1 again. Why it's 1? Because the numerator and denominator, if I change, I put the 3 here, then it's the same. Okay, so then as the limit is to be 1/3. Okay, how do you solve this? You divide the numerator denominator by n squared. So 3 minus 2 over n squared is 2 over n is 5 over n squared. So the limit is 1/3, which is not going to be 0 again. So when n sufficient large, every time you add a term will be very close to 1/3. That's why the sum is getting bigger and bigger and bigger. And it goes to infinity. So that's why it's divergent. Now, if you can also say that, not only divergent, you can say that this is a positive infinity. Okay. All right. All right, so let's take a look at the next problem. Okay, so look at this. My question is it convergent or is it divergent? Look, the nth term is going to be nature log 1 over n is the 1, right? It's going to be nature log of 1, which is 0. So the nth term approaches 0. The nth term is positive always because n plus 1 over n is greater than 1. Okay? Is it convergent? You cannot use the nth term test for divergence to prove it is convergent. You can only use that to prove it's divergent. But right now, the limit is 0. The limit of the nth term is 0. So you cannot say anything using above theorem, okay, if you know the logic, right? My question is, are you able to figure it out using other methods about its convergence, whether it's convergent or divergent? All right, so think about this. I'll give you a minute. Okay. We haven't learned enough theorems to get some conclusion. Okay. You will see that why it's getting more and more difficult, because you have to prove whatever you claim. That's it. You know, you are as a lawyer, acting like a lawyer. Remember that in this chapter, you are acting a lawyer. If you claim it's divergent, you prove it's divergent. Use the evidence. You have to, after you provide the evidence, you have to quote the theorems you already learned in the book. You cannot create a theorem. You cannot create a law to prove someone is guilty or not guilty, right? But you have to collect enough evidence, then call some, cite, some laws, then you can show, okay, according to this law, it's guilty, but you need to provide evidence too. So this is the idea. That's why it's difficult. Otherwise, everybody can become a lawyer, right? But let's try. But in mathematics is different. You don't need to memorize things sometimes. Everything's in logic. Okay. Here, we don't have enough, but we have to know that we know the definition when it's called divergent, when it's called convergent. So you take a look at the partial sum. This, we go back to the original, right? So if by definition, the series is convergent if this partial sum is a limit. Sometimes we are lucky. We can find the limit of the sum if we are able to combine all the terms. Look at these terms: natural log 2 over 1, right? The first term. Natural log 3 over 2. Natural log 4 over 3. The last term, natural log of k plus 1 over k. Okay, well, you have a k terms, but those k terms can be combined into one terms, right? And here's a 4 over 3. And this is a k of k minus 1, that's k plus 1 of k. Then you realize that, oh, there are lots of terms can be canceled out. 2, 2, 3, 3, 4, 4, and this term, right? So only one term is left, which is natural log of k plus 1. Now it's obvious this goes to infinity as k go approaching infinity. Did you figure out this? Okay. And then the limit of sk is going to be infinity. Okay. So the series is divergent. Okay. There's a difference between series and sequence. Given a sequence, you add them together, all the terms, you get a series. And when you're talking about series, you have to make sure the limit of the new sequence is convergent. Okay. So given a series, right? So yeah, given a sequence, okay, we get a series. Series is a sum of these terms. In order to check this series is convergent, divergent, then we consider a new series, a new sequence. Okay, that's SK, which is this. Okay, so if this new sequence is convergent, then we say this series is convergent. Okay. Okay, and then this series, by definition, is going to be the limit of this sequence. Okay, that's a lot. Okay, and if the series is convergent, then so right now to prove it is convergent, you can only use the definition. We don't have any other theorem we can use. But prove it is divergent, then we can just check the nth term. Sometimes the nth term approaches 0, then it's a divergent. But unfortunately, for the above problem, the nth term, the limit is 0. We still see that the series is divergent. Okay, so the limit of the nth term is 0 does not guarantee the series is convergent. And here's another example. Okay, here's another example. Okay, here's another example. Okay, and then this one, the limit is 0, but the series is divergent. Okay, then how to prove it's divergent? It's not easy to do that. Okay. Okay, we are going to prove that in next section. Okay. It will be. We have to prove it, right? I claim it is divergent. We proved in the section 11.3. We're going to learn a theorem, very powerful theorem, and we can prove that it's there. Okay. Yeah, and even this one. This one, even this one is divergent. Okay, even this one is divergent. And 1 over n, and why it's divergent? Yeah, this one is a little bit easy to prove, but we better to reserve this problem to next section. Okay, so now I'm going to look at the following problem. All right. Is this convergent or divergent? Well, the first term is 1. All right. All right, let me show you how to do it. And clearly the limit of the nth term is going to be 0, right? So I cannot use that to prove it's divergent. So I cannot use it to prove it's divergent, right? Because this is a test for divergent. Test for divergence here. So maybe it's convergent. Okay. So just look at the partial sum. Okay. Well, the partial sum is going to be 2 squared minus 1, 3 squared here minus 1 here, and the last term is k squared minus 1. Is there any way I can combine them? Maybe, I don't know. Right? Now, when you see n squared minus 1, you should know n squared minus 1 is n minus 1, n plus 1. That's very important. Okay? If you're using that fact, then, and also should know that similar to the above one, it's going to be n, here, n minus 1, n plus 1. So can I decompose it into two parts? The answer is possible, but when you combine them, I get 2 on the top, right? 2, because n plus 1 minus n minus 1 is 2. So I have to divide by 2. And that's a key step, okay? So I will get the first term is a 1 minus, I think it's going to be, and when n is 2, right? 2 plus 1 is 3. Okay, that's first term. And then it's 1/2 minus a quarter. Okay, the difference between those two integers will be 2, right? And the third term is, okay, every term here is divided by 2, 1/2. One over 6, and keep it going. So the last term here is a k minus 1 minus k plus 1, 1 over k plus 1. So anyway, you can, it's harder to cancel all the terms here, but look at the first term in each parenthesis, right? You can have a 1 over 1, 1 over 2, 1 over 2, one over 2, and here's a 1 over 3, 1 over 4, and keep it going, right? And then you minus half of them, put all the negatives here. 1 over 3, 1 over 4, 1 over 5, and then it's easy to figure it out. 1 over k plus 1, right? Then you will see, oh yeah, maybe those terms will be gone, right? Okay, yeah, that is true. So you have 1 plus 1/2, 2 terms left. So here also 2 terms left. Okay. Then you will see k. Okay, the last 2 terms approach 0. This is partial sum. It approaches 1/2, 1 plus 1/2. Okay. So that will be 3 over 4. Okay, this is my answer. Okay, so now I come, yeah, where's my original one here, right? It's yeah, this is a SK, right? You know, yeah. So the limit k approaches infinity. This is just 3 over 4. Right? So that will be the answer. And that will be the answer. So right now, if you cannot, you can use a geometry series to check whether series is convergent or divergent. You can use the nth term test to prove some series is divergent. You can also use the original definition and try to find the limit of the partial sum. Okay, and then the partial sum has a limit, then it's convergent. Even you can figure out the sum, right? If the partial sum does not have a limit, then it's divergent. Okay, So that's it. And now we are almost to the end of the class.